So my main concern to solve this problem, to obtain the value of u at any point inside the domain. To do that, I will start with the indirect formulation. Indirect and discrete formulation. Indirect and discrete formulation. To do that is very easy. What I'm going to do, for example, if this is my problem, I will demonstrate what I'm going to do on numerical example. I will take each side, this one equal to 4 meter, for example, and this side also is equal to 4 meter. Okay, so I will choose a point on this boundary, and I will choose a point on this boundary, choose point on this boundary, choose point on this boundary, represent the overall boundary. I can choose more than one point, but for simplicity now, I'm going to choose just a single point at this boundary. This point will be x1, this one will be x2, this one will be x3, and this one will be x4. Just I want to put x2 near the boundary. This is x2. In order to solve this problem as we did in bars, what I'm going to place, I'm going to place 4 sources. So I'm going to place source here, I'm going to place source here, I'm going to place source here, I'm going to place source here. Practically, we don't have this problem now. This is problem in infinite domain. Actually, we don't have the problem. We have the problem in infinite domain. And all of this area is infinite domain. What we have here is infinite domain. And there is, we just put lines here to represent our problems. We have nothing, actually. So this one is xi1, this one is xi2, this one is xi3, and this one is xi4. I'm going to separate these xi's. I can place it at any place I want. Just I'm going to put it with 4 meter also. I can put them anywhere I like. Anywhere I like. So I knew very well from potential problem, if I come back to this differential equation, I have this differential equation, I have associated fundamental solution with it. So if I have nabla square u asterisk of x and the xi equal to minus delta of x and xi, the solution of this problem, you have to believe me now, u asterisk of x and xi equal to minus over 2 pi ln r between x and xi. Okay, if I'm going to differentiate this one to compute q asterisk of x and xi, so it will be the derivative of, with respect to x alpha of x to u asterisk of x and xi times n alpha, because we knew the derivative with respect to n, remember this, the derivative with respect to n equal to the derivative with respect to alpha times n alpha. This is, sorry, here is alpha. This is what I did here. I differentiate with respect to x alpha times n alpha of x. When we do that, it's very easy. The derivative of ln, it is 1 over r, and the derivative of r is r comma alpha times n alpha, it will be r comma n. So directly, we will have 1 over 2 pi r comma n. Actually, it is r alpha, this is r alpha, r comma alpha times n alpha. It will give me directly r comma n. Coming back here, so each source here will have intensity, a certain intensity. For example, this source, it has a certain intensity. This source with intensity, we will call it phi. For example, this source, it has intensity called phi. phi of xi1. Phi of xi1, I'm going to give it the name phi1 direct. And the same, this source, it will have phi of xi2, and so on, so on, so on. So each source will give effect here, will give effect here, will give effect at this point, and the last source will give effect at this point. Okay? Every source will give effect for U and will give effect for Q. Straightforward. We can write direct. We can write U of X equal to the summation on the sources. I'm going to give with the name I, and I goes to 1 to 4. To the fundamental solution between X and the xi times the phi of xi I. And the same Q of X, if I want to differentiate this with respect to the derivative here, with respect to x alpha of x, and then I will multiply by n alpha of x, it will give me direct this superposition equation q asterisk of x and xi times the phi of xi. Remember, I'm going to differentiate this one to give this one. This is constant. The phi of xi is constant because my derivative here is with respect to the coordinate x alpha of the point x. And I knew very well, I knew the analytical expression of u asterisk, and I knew the analytical expression for q asterisk from this slide here. Here we have them. We have these two expressions here. Okay? So we knew from my fundamental problem, still I have infinite domain. I put lines to represent my problem. I put lines to represent my problems. And I put single point at each side, x1, x2, x3, x4, to represent my problem. Here I put here, this is actually, this is x3, I'm sorry. And this is x4, it's okay. You can choose any orientation, any notation, anything you like. And I knew that at each point on the boundary, here we have no boundary actually. These are lines to represent my problem. Okay? So I knew the potential or the value of the heat, the temperature, U of X, at any point x1, x2, x3, x4, I knew very well it will be the superposition from all sources I placed. Okay? For example, if I want to write this equation at point x2, let's just choose point x2 for example. We will choose point x2. If my choice for point x2, I can write directly that the potential U at point x2 equal to U asterisk between x2 and xi1 times the phi1. I'm going to write it phi1 direct. Phi1, it means the phi, the intensity of the source at xi1. As we said, we are going to abbreviate it direct. Plus U asterisk between the point x2 and the other second source, phi of xi2, which is phi2, plus U asterisk between the point x2 and xi3, phi at xi3, plus U asterisk of x2 and xi4 times the phi at xi4. Let us see in this equation where are the unknowns and where are the knowns. Okay? Until now, I knew very well that these phi's are unknowns. So phi1, phi2, phi3, phi4 are unknowns. All of these phi's are unknowns. Okay? The value of the fundamental solution itself are known. All of these values are known. Okay, for example, let us take this value. Let's take this value. This value, it is u asterisk of x2 and xi1, which means it is equal minus over 2 pi times ln r between point xi2 and xi1. Where is the r between xi2 and x2 and xi1? The r between point xi2 x2 and xi1 is this one. I'm going to draw it here with red. Here is xi1 and here is point x2, so it is here. It is here. Just 1 second. This one. This is r between x2 and xi1. This one is the red one here. The value of r here is very well known. It is square root of, the horizontal one is 2 square plus, we have 4 here and 2 here plus 6 square. So it is very well known. So this r is very well known. So this one is known. Okay, and this one is known, and this one is known, and this one is known. So now I have in this equation the intensities phi1, phi2, phi3, phi4 are unknown, and all values of the fundamental solution are known. And what about the value of u at x2, the temperature at x2? Remember the question itself, u at x2 here is equal to 0. So it is very well known here, this part is equal to 0. So we have now the first equation, we have the first equation at xi2. Let us write the same equation. I want to write the same equation at xi1. I want to write the same equation at xi1. So at, no, I want to choose the other color. So at x1, sorry, at x1, not xi1. At x1, here I can write the same equation at x1. If I write the same equation at x1, I will have u at x1 equal the fundamental solution between x1 and xi1 times phi1 plus u at x1 and xi2 times phi2 plus u at x1 and xi3 times phi3 plus u at x1 and xi4 times phi4. Where is the known and the unknown? Still, these phi's are unknowns. The intensity of the phi's are unknowns. All of them are unknowns. And the fundamental solution are known. We can compute them. But what about the value of u at x1? Let us see u at x1 here. Here is x1 at this side. So u at this side, u at x1 here at this side is unknown still. When you Q actually, when you Q the flux at this side, at x1, when u the flux at x1 is equal to 0. So this equation is not good to be used. So this equation is not good to be used because this is still unknown. So we still have the same unknown values for phi's and still have extra unknown here.